It's my pleasure to present our work in this international conference in the category Best Research Award. I am the Associate Professor Ana Clarissa Pires from Food Technology Department of Federal University of Viçosa in Brazil. I will present to you our scientific work entitled Beta-casein monomers as potential flavonoids nanocarriers, Thermodynamics and Kinetics of beta-casein naringin binding by fluorescence spectroscopy and surface plasma resonance. Our research group has a major question. How do the dynamic and stable energetic parameters determine the supramolecular complex formation process? Answer this question is very important to deliver interesting molecules in different matrices, such as food, medicines, cosmetics, among others. Also, answer this major question is important to answer minor but important questions. Are the complex formed between proteins and bioactive molecules stable at different temperatures? Which protein is the most appropriate to deliver each molecule? What interactions drive the complex formation? And how long do the complex take to form and to dissociate? Let's see. Recently, people are more concerned on their health and well-being. Everybody wants to age well. Thus, there is a growing demand for healthy, nutritious, but also tasty foods. Bioactive molecules can be extracted from different vegetable sources, and the use of these bioactive molecules as health promoting is promising. However, there are some limitations, such as stability, solubility, and flavor of some bioactive molecules. For example, naringin is the flavonone glycoside responsible for the bitter taste in lemons and grapefruit, and is found in many citrus fruits. It shows antioxidant, anti-inflammatory, and anti-obesity properties, and has also demonstrated potential in mitigating metabolic complications in HIV patients. Thus, naringin activities show potential for application in the food and health fields. But naringin is hydrophobic, bitter, and has low chemical stability. To enable the efficient vehiculation of small hydrophobic bioactive molecules in different matrices, the interactions of such molecules with food proteins have been studied. In this case, food protein acts as a glove to protect the hydrophobic molecule of contact with water, and increasing its solubility, for example. Beta-casein is an intrinsically unstructured and flexible protein of 24,000 grams per mole with high content of proline residues that disrupt the formation of its secondary structure. Beta-casein has been used as carrier for many bioactive molecules, mainly hydrophobic bioactive molecules such as naringin. But why use beta-casein to deliver bioactive molecules such as naringin? It has high nutritional value, it also has a hydrophobic region, and it can form micelles at specific thermodynamic conditions such as temperature and concentration. A micelle is a molecular self-assembly structure that has a hydrophilic layer that protects the large hydrophobic core where hydrophobic molecules such as bioactive molecules can be placed. In this context, our objectives were to provide detailed comprehension of the thermodynamics of beta-casein naringine binding occurring close to the tryptophan residue of beta-casein by fluorescence spectroscopy. Beta-casein has a tryptophan that emits fluorescence. Thus, fluorescence spectroscopy is an attractive technique to investigate interaction between protein and bioactive molecule. We also aimed to provide the kinetics and thermodynamics of beta-casein naringine binding by surface plasma resonance. And finally, we aimed to provide a fundamental basis for the naringine incorporation in different matrices using beta-casein monomers as vehicle. For the fluorescence experiments, we added aliquots of naringine solution into beta-casein solution, both at pH 7.4. Then we analyzed the fluorescence emission by protein at each concentration of naringine. We fitted this model to the fluorescence spectra data, where the independent variable is this term and dependent variable is this term. Using this approach, we could determine the binding constant and the complex stoichiometry of the complex. The binding constant is a relationship between the complexes and the free molecules in the system, while the complex stoichiometry gives us information about how many molecules, naringine molecules, are bound to each beta-casein. Using the binding constant, we could calculate thermodynamic parameters of complex formation. For example, we calculated the standard Gibbs free energy change, which indicates the direction of this chemical equilibrium. We also determined the standard enthalpy change and the standard entropy change. They provide information about what kind of interaction drives the complex formation. For example, is the complex formation an endothermic or an exothermic process? For the SPR experiments, we immobilized the beta-casein on the surface of a gold chip. Over this immobilized protein, we flowed solutions with different concentrations of naringine to obtain a sensorgram for each naringine concentration. This sensorgram shows us a different molecular process. For example, at step 1, when only buffer flowed over the immobilized protein, we have the baseline. When the naringine solution started to flow over the beta-casein, we have the association, mainly the association process. We can observe that the resonance signal starts to increase in the association process. It increased until activate the metastable equilibrium, where the velocities of association and dissociation process are equal. After, again, the only buffer flowed over the immobilized beta-casein, so the dissociation process dominated until the resonance signal returns to the baseline. We fitted this model to the SPR data to obtain the kinetic constants. The association kinetic constant, Ka, expresses how many complexes are formed each second, while the Kd is the dissociation kinetic constant express the percentage of complex breaks up every second. Applying the Arrhenius approach on these kinetic constants, we can obtain the energetic parameters for the activated complex formation. This activated complex formation is an intermediate structure between free molecules and thermodynamically stable complex. Determining the energetic parameters for the activated complex formation allow us to know about the molecular dynamics of the complex formation, of the stable complex formation. It is a very important information. By the relationship between kinetic constants, we could calculate the binding constant, which is a thermodynamic parameter. And using these previously discussed equations, we could calculate the other thermodynamic parameters from the SPR experiment. From the fluorescence experiment, we can see that there was fluorescence quenching, which means that naringine quenched the fluorescence emitted by the protein. However, this interaction between naringine and protein did not displace the maximum wavelength of fluorescence emission. You can see here. This indicated that there was no significant conformational change in the tryptophan binding site. The fluorescence quenching is due to collisional or static mechanisms. The static mechanism is the main responsible for the complex formation. Thus, to know if our fluorescence data was due to the static mechanism, we fitted the Stern-Volmer model to the fluorescence intensities data. We can observe that there was a linear fit of Stern-Volmer model, and also we could obtain the biomolecular constant of suppression. This value was higher than the maximum of value obtained through collisional mechanism, so we could conclude that β-casein and naringine formed a complex. The binding constant for the β-casein naringine complex was around 10 to 4th liters per mole, which is an intermediate binding constant. There are processes that has a remarkable higher binding constant. For example, the interaction between an enzyme and its substrate shows binding constant around 10 to 10 liters per mole. The complex stoichiometry was around 1, which means that there was 1 naringine molecule to 1 β-casein molecule. The delta G values were negative at all temperature that we studied. These negative delta G values indicated that there were more complexes than free molecules in the system. We can also observe that the higher the temperature, the more negative were delta G values, which indicated that complexes were more stable at higher temperature. It's an important result because the higher stability of the naringine, the β-casein naringine complex, occurred near our body temperature. Regarding the enthalpy and entropy contributions, we can see that they were positive, indicating that the complex formation was an endothermic process. Also, it emphasized the hydrophobic effect for the process, for the complex formation. And these values, these positive values, show us that dissolution energy of interacting molecules overcame the energy released from a specific interaction between β-casein and naringin. From the SPR experiments, we can observe that the higher the naringin concentration, the higher the resonance response, indicating that there was a formation of complex between β-casein, immobilized β-casein, and naringin. Starting to analyze in Table 1, we can see the kinetic constant values. They show us that at each second, around 2,300 complexes were formed, while 30% of them dissociated. In Table 2, we can observe the kinetic parameters related to activated complex formation. This activated complex formation is formed from association of free molecules or dissociation of thermodynamic stable complex. We can observe that delta G values for the dissociation phase were higher than those found for association phase, which means that β-casein and naringin molecules associated faster than the stable complex dissociate. These higher delta G values for the dissociation phase is mainly due to the protein conformational change of thermodynamic stable complex to form the activated complex. Even the enthalpy cost was higher at the association phase. Returning to Table 1, we can observe that binding constant values were of the order of 10 to 30, which were smaller than those obtained by fluorescence spectroscopy. The delta G values were also negative, but a little bit smaller than those obtained by fluorescence spectroscopy. And delta H and T delta S values were positive, but also different from fluorescence results. This is important because with this result by SPR experiment, we can conclude that there was at least one more site for naringin interaction in β-casein, not only the tryptophan binding site. These positive values also emphasize the hydrophobic effect responsible for the formation of the complex, and this hydrophobic effect can be attributed to the dissolution of molecules to form the complex. Here we can see the release of water molecules when the naringin interacted with β-casein. This is the dissolution process. So from this work, we can conclude that interactions between β-casein monomers and naringin occur close and far from tryptophan residue of β-casein at pH 7.4. The β-casein naringin binding process occurs with a key role of dissolution of free molecules, evidencing the occurrence of hydrophobic interactions. SPR data demonstrated that stable β-casein naringin complex formation occurs via an intermediate state at which an activated complex is formed from the association of free molecules or dissociation of the thermodynamic stable complex. The speed of interactions is dominated by β-casein conformational chains. And finally, the thermodynamic and kinetic data supplied from this study provide valuable information on the dynamics of complex formation between small bioactive molecules and intrinsically unstructured proteins, allowing future applications of similar complex in the food and health fields. I'd like to thank all the authors of this work for the partnership. I also appreciate the infrastructure and support provided by Federal University of Viçosa and Therma and Kivecon groups. I'd like to thank the founding agents responsible for the support, the financial support for this work, and I'd like to thank you for the attention. You can find our original paper in this address. Thank you.